Hi there. In this video we're going to look at matrices and how we apply transformations represented as a matrix to a particular vector or vectors. Okay, so if you've not watched last video, I recommend you go in and watch that because it goes through where we get these transformations from, and we're going to look at that to sort of figure out what this might look like in the context of matrices and as a procedure. So let's have a look then. First of all, just what this transformation looks like, and then how we can apply that to a vector. Okay, so remember this is, which way around did I do it? This is I hat, and the image of I hat, and this is the image of j hat. So I hat starts at 1, 0 and ends up at 2, 0. So that's the image of I hat, and then the image of j hat, well, it starts at 2, 1, 1, 0, 1, sorry, and it ends up at 2, 2. So image of j hat, image of I hat, and I hat. Okay, so let's have a think then. So it sort of expands it out and it shears it, it sort of pushes it over to the right a bit. So we're sort of expecting this vector 3, 4 to end up over here somewhere. It's been made a bit bigger and it's been shoved to the right a little bit. But just sort of saying what we expect it to do probably certainly isn't rigorous enough for what we want to do. And so remember from the first video on this, we said that this vector 3, 4 means that it's 3 lots of I hat originally, and it's 4 lots of j hat. So to figure out where this goes to, so after the transformation, it might make sense as if it's the vector 3 times by this new I, the image of I hat, and I need that pen, 4 times by the image of j hat. Okay, and actually it doesn't make sense as a vector, so we'll cut that bit out and we'll... Okay, so it might make sense then to think of where this vector ends up at. If it was originally 3 times I hat and 4 times j hat, then after the transformation, it kind of makes sense to call this 3 times by the image of I hat and plus 4 times by the image of j hat. Now what does that look like? Well, that's 3 lots of 2, 0 plus 4 lots of 2, 2, and which gives me 6, 0 plus 8, 8, which is 14, 8. So 3, 4, if we apply this matrix transformation to it, ends up at 14, 8. So what we'll do in the next little bit is sort of see how we can generalize this and give ourselves a slightly more efficient method so that we don't need to do this every single time. But I think it is important that we sort of see where this is coming from. Okay, so we're going to have a little bit of a look and a bit of a review of exactly what we did, and then we're going to see if we can come up with a method that sort of lays this out in a little bit more an intuitive way for us to work out, rather than having to expand it each time. Wouldn't it be lovely if there was some sort of algorithmic method we could follow to embed all that information and spit out the answer? So what we're going to look at first of all is exactly where this 14 and this 8 came from. So let's first of all just look at where this 14 came from. So you recall that we did 3 times by 2, 0, and we added on 4 times by 2, 2. Okay, and if you see, this matrix has just been split into these two vectors here. Now this top number, 14, came from the 3 times by the 2, and it came from the 4 times by this other 2. So the top number in this vector over here only depends on the top row of this matrix here. Okay, and similarly this 8 came from the 3 times by the 0, and it came from the 4 times by this 2. So again, this bottom number in our vector only depended on the bottom row of our matrix. So what we can do, a handy little method that I quite like, again this is similar to the grid method of multiplication. So if you're in a non-calculator paper and you're doing some working out, over to the side you might draw a line for some rough work and you do a grid method. This is the same as that. This is sort of goes in your rough workspace. This wouldn't go as part of a logical argument. And what we can do, 2202, if we lift up the 3, 4 to above it, that gives us this handy square here, which we'll talk about a little bit more later on. But what that means is this number here is this row times by this column, so 2 times 3 and 2 times 4, which is my 14. And this number here is this row, also times by this column. Okay, so 0 times 2, or 0 and 0 times 3 and 2 times 4 gives me the 8. Okay, so this is the method that I'm going to use. You can, if you don't want to do this method, you can just think, well, the top number is the top row times by the vector, and the bottom one is the bottom row times by the vector. But I really like laying it out like this. I think it's really nice and easy to visualise. So we'll look at a few examples next then of how we can just procedurally answer some of these questions. Now, in the back of your mind for all of these, you should be thinking that this matrix represents a transformation of a vector. So every time we're just thinking, where does this vector end up at after it's done this matrix? But this is sort of the foundation of matrix multiplication and the methods behind it. That's good. Okay, so on to our second example. So I've written these as multiplications. Again, just think of them as transformations. I'm going to go through this one, and while I'm going through this one, if you follow along with this one, and we'll see whether we get the right answer. So again, my question is that I've got this transformation matrix 2, 3, minus 1, 1. And now here we're a little bit away from your simple rotating by 90 degrees or reflecting in line y equals x. This transformation is going to look quite complicated, but because we've got this method of matrix multiplication now, we've got this way of doing this problem. So I'm applying this transformation to this vector minus 2, 1. It's a very similar question for you guys. So what we'll do is, remember, in your rough working out space, we've got 2, 3, minus 1, 1. I want to do minus 2, 1. So remember, the top number is this row times by this column. So we do 2 times minus 2 is minus 4. And we do 3, let's do that a bit bigger so you can see, minus 4, and we do 3 times by 1, which is 3. And we'll do the accounting and work that in a second. Let's just get the bottom row of our vector here, and that should be a minus 1 there. So now the bottom number is this row times by this column. So we get minus 1 times minus 2 is positive 2, and we get 1 times 1 is positive 1. So this is equal to minus 4 plus 3, 2 plus 1. Just literally take that vector over here. Now let's work that out. Minus 4 plus 3 is minus 1, and then 2 plus 1 is 3. So if we apply this vector, or apply this transformation matrix to this vector, it's going to move to minus 1, 3. So it's sort of going to squish it in that way and stretch up that way. So in a second, we'll just sort of check your answer to that. Now's a good time to pause the video if you need a chance to catch up. Okay, so let's have a quick look at this one then. So again, working out space, 3, 4, minus 2, 6. 1 minus 1. So the top number is this times this. 3 times 1 is 3. 4 times minus 1 is minus 4. The bottom number is this times this. Minus 2 times 1 is minus 2. 6 times minus 1 is minus 6. So then we get this is equal to 3 minus 4 minus 2 minus 6, which is equal to, well, 3 minus 4 is minus 1, and minus 2 take away 6 is negative 8. There's a really subtle point, I suppose, here, and that I think I want to highlight, is that 3 minus 4 is one entry in this matrix, or it's a vector, isn't it? It's a 2 by 1 matrix, but that's just one entry in this matrix, whereas here, for example, the 3 and the 4, they're separate entries in a bigger matrix. So here we can work this out, but let's just pretend for a second that that was negative 4. You couldn't go and do 3 minus 4 and replace that with negative 1. That wouldn't make sense. It only works here because it's one entry in this matrix. It's not 2 separate entries. But if you did manage to get that at home, well done. That's really good. Okay, so now we're looking at applying this matrix here, 1, 3, minus 1, 2, to the shape ABCD, which is a triangle. And it's made up of 3 coordinates, okay? So what we could do, and what I've seen people try and do before, is apply 1, 1 to this matrix and write that down, apply 1, 3 to this matrix and write that down, and then apply 3, 2, or apply this matrix to 3, 2, and then write that down and do it all separately. But handily, now we've got this method, we've got a really nice way to generalise this to more vectors. Okay, so let's have a bit of a look then. If we do 1, 3 minus 1, 2. Now, as a vector, this is 1, 1. As a vector, this is 3, 2. And as a vector, this is 1, 3. And so what we can do, instead of dealing with these all as separate vectors, we can lump them together into one matrix that has all 3 of those vectors in it. So we'll do it in the order ABC. So A is 1, 1, and that's going to be the first entry in our matrix. B is 1, 3, that's going to be the second entry in our matrix. And C is 3, 2, that's going to be the third entry in our matrix. Okay, so now what we can do is we can multiply these 2 matrices together. And what we'll do is we'll just generalise a little bit the method we used before to work this out. So again, working out space, I'll do the working out space down here. We're going to lift this matrix up. So above, so we've got our space for an answer here. And again, that gives us a handy square there. In the next video, we'll look at why it's important to check that that's a square. But for now, I think it's good enough that we just know that it's a square. And what we'll do is we'll work out this matrix. So this entry here is going to be this column times by this row. So we're going to get 1 times 1 is 1, 3 times 1 is 3. If we add those together, it gets us 4. So I'm not going to write out the full working out here. I think we've sort of had enough practice with that. If you do need to pause and just sort of convince yourself that this is right at any point, then feel free to do so. Okay, so now let's look at this entry here. So this is this row, minus 1, 2, times by this column again. So minus 1 times 1 is minus 1. 2 times 1 is 2. Minus 1 plus the 2 is 1. Okay, so now let's look at this next entry up here. So this entry here is this column times by this row. So we get 1 times 1 is 1, 3 times 3 is 9, 1 plus 9 is 10. And similarly, we get this column times by this row. 1 times negative 1 is negative 1, 3 times 2 is 6, 6, take away the 1 is 5. And now let's look at this last column here. We've got 1, or we go this row, sorry, times this column. 1 times 3 is 3. 3 times 2 is 6. Add those, we get 9. And then this row is going to be, or this entry is going to be this row times by this last column again. So with each of these entries, we're always looking at the row that's next to it and the column that's above it. So minus 1 times 3 is minus 3. 2 times 2 is 4. Minus 3 plus the 4 is 1. Okay, so this is our answer to this matrix multiplication here. So we get 4, 1, 10, 5, and then 9 minus 1, or 9, 1, sorry. So what that tells us is this triangle is transformed where the image of A is 4, 1, the image of B is 10, 5, and the image of C is 9, 1. And if we had a big enough grid, we could draw that out fairly accurately. Let's just do a quick sketch of what it would look like. So the furthest one away is going to be 10, 5, which is going to be here. 4, 1 is going to be down here. And then 9, 1 is going to be over here. So that's what our triangle looks like after it's been transformed from this guy. Remember, this triangle is quite close to the origin. It sort of started over here, didn't it? So that's sort of where it goes. So yeah, good. So I think we'll make that the last example for this video. In the next video, we'll look at sort of we've already looked a little bit at generalising this, but we'll look at how we can fully generalise this method of matrix multiplication, and then check in to see whether a matrix will actually multiply or not. Very good.